Okay, let's start. Let me quickly revise what we did yesterday. So, day before yesterday, um, we learned that if you have an analytic function, a function analytic everywhere, then you can write a series for it like this: 0 to infinity a n z to the power n. Okay, this is around z equal to 0. I hope you did for z equal to z naught. It's just replacing z to the power n with z minus z naught to the power n, and all the derivatives and all you need to calculate at z naught. And then a n, we found two different formulas for a n. For this case, this is integral 1 by 2 pi I dz f of z divided by z to the power what? N plus 1. Excellent. But there was another formula, right, which was 1 divided by n minus 1, 1 divided by n factorial nth derivative of f of z, calculated where? Where do you calculate this? At z equal to 0. Right? So this was if the function was analytic. If the point where you are from, the point around which you are expanding was not analytic, but rather a pole or an essential singularity, then you need to include what? Negative powers also, right, to account for that. Okay, so then you get f of z to be sum n runs from minus infinity to infinity a n z to the power n. Okay, where you have negative powers as well, right, which will cause the function to what? Blow up. And the negative power part will tell you whether it's an essential singularity or a pole. If it's an essential singularity, then all the negative coefficient, all the a's with negative indices, right, a minus 3, a minus 5, would be non-zero, right? If it's a pole of finite, or if it's a pole of finite order, then up to that order it would be non-zero, and after that it will be 0. And all an's you can find by using the integral formula. This you have to consider loop around z equal to 0, because z equal to 0 is the point you are expanding around. Okay, dz f of z, this derivative trick won't work anymore. Okay, because negative powers will cause problems. Okay, but then we learned an important thing, that there is a special coefficient a minus 1 here, right, which we called residue, and it gave us the integral of the function around this point of around this isolated singularity. Okay, so we found out that, say, if you substitute n as minus 1 here, you will get a minus 1. It is just directly. So a minus 1 is 1 by 2 pi I integral dz f of z. So integral of the function around this isolated singularity, okay, is nothing but the a minus 1 coefficient, right? That's why we gave it a special name. We called it residue of the function. Okay, and there was a way to compute this residue without expanding the function. Okay, provided you have a what? Pole of finite order. You have a pole of finite order. Okay, if you have a pole of finite order, then the residue a minus 1 is basically 1 divided by n minus 1 factorial limit z approach to 0. This limit was necessary because, right, because z to the power n f. So this was basically, we used this formula, this thing, but we needed to make the function analytic first. Since it had a pole of finite order, I multiplied with z to the power n. Finite order means maximum negative power that will come in f of z is 1 by z to the power n. That will be cancelled by this, and that's exactly why we need to take this limit. Okay, and for simple pole you don't need to take the derivative. It's just for n equal to 1, the simple pole, the residue is, this is for simple pole, it's just limit z approach to 0 z f. And if it is at z naught, then z minus z naught times f of z. Okay, so this was basically the integral of the function over this over a closed loop surrounding this non-analytic point. Okay, then we learned that if you have any any loop containing any number of non-analytic points, all you need to do is compute residues around every point, right? So residue, so if you have some this and you have non-analytic points here, 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 wherever, okay? So you need to find a minus 1 when you are expanding around this point, a minus 1 when you are expanding around this point, a minus 1 when you are expanding around this point, add them, add these residues, that will give us the total integral f of z dz 2 pi I times sum of this. So if all of them are poles of finite order, all you need to do is this formula, 1 divided by n minus 1 factorial limit z approach to, let's say, zi, let's say this is z0, this is z1, z0 is just 0, this is z2, z approach to zi, nth derivative, n minus 1 derivative, right? Z minus zi times f of z. So you do this and then take the derivative, okay, and then limit z approach to zi. These limits are usually simple to take, so not very complicated limits, okay. The reason we took the limit is because f of z contains 1 by z minus zi, so you can cancel them only when you are in the limiting case, not when you are exactly at zi, okay. So integral of the function around this closed loop is just 2 pi times sum of this. So this was the crux of yesterday's class. We'll come back to this and we'll use this to compute real integrals. That is essentially a major use of this formula, okay. But for now, let's think about a bit more about this series that we wrote, okay. So we wrote a series, okay, which contains what? Negative powers and positive powers, and we called it what? Laurent series. It's called Laurent series, okay. Now we'll speak about when does it give finite answers. So when does this series converge, right? It can't, you adding positive powers and negative powers, it can't always give you like a finite answer, right? There must be some, okay. Let me write down the series. 1 plus z square plus so on. Okay. Is this a series? Yeah, it is, right? Is this a series like the one we considered earlier? Yes, all the ANs are just 1. Okay. Okay. Huh? In fact, it is analytic also, right? Right? Huh? It is analytic, right? Huh? Where is it analytic? Is it analytic everywhere? We'll see. We'll see. Okay. Huh? So when I add this, what do I get? It's a GP, right? Huh? So it is equal to 1 divided by 1 minus z, right? Isn't it? Right? If you add GP, mod z square, mod z cube, whatever. Sorry, z1 plus z square, whatever. Right? It's equal to 1 over 1 minus z, right? GP. Is it always equal to this? Whatever z is. Whatever z is. The answer is, huh? Okay, think a bit. You are adding powers of z, right? Let me use polar form, then it might be easier. So 1 plus r e power iota theta plus r square e power what? 2i theta plus r cube e power. So you are adding powers of z, right? This is innocent, this e power iota theta. It just oscillates. It does nothing else, right? It is just sine theta and cos theta. It's sine n theta, cos n theta. And sine thetas and cos thetas are always bounded between -1 to 1, right? They can't take values beyond that, right? What might cause problems here? R would cause problems here because you're raising R to the power, raising R to higher and higher powers, right? And then adding, okay? Huh? Right? So if R were, let's say, 2, will it give a finite answer? So 2 square, 2 cube, 2, huh? It'll give an infinite answer. Right? It'll give an infinite answer. Okay? It won't give a finite answer. Is that? Huh? So what should R be so that you get a finite answer? What do you think? The subsequent, I mean, there is a very precise way of saying this, but let's say, we'll do it with simple intuitive way, is that R should be such that when I take powers of R, it should become smaller and smaller. So what kind of R should that be? What numbers when you raise them to the power will become smaller? Huh? Less than 1. Less than 1. You are indeed right. So this series will give you a finite answer only when what? Huh? But R is not mod Z, right? Okay. So this series is equal to this only when mod Z is less than 1. Okay. You know? Because let's say R is half. Half square is 1/4. Half cube is 1/8. And then it becomes smaller and smaller. Okay. Is that fine? Huh? So this series converges when mod Z is less than 1. Okay. And in fact, this I can write series where mod Z is less than some let's say capital R. If, for example, let me write f of Z. We'll discuss this in general, but first let's get this intuitive feel of what is happening. So 1 plus Z by R plus Z square by Z by R whole square plus so on. When do you think this will converge? When do you think this will give you finite answers? When R is what? When see here you wanted mod Z to be less than 1. This is exactly the same thing, but you have Z by R. So you want mod of Z by R you assume to be a real number, some real large number. Let's say R is 100 or something. Okay. So when will this give you a finite answer? Huh? Mod Z is what? Mod Z is less than 1. Mod Z is less than R, exactly. So it will give me a finite answer when mod Z is less than R. Assume R to be some positive number, 100, whatever. So this is essentially the same series, but you see now the coefficients are different, 1 by R, 1 by R square. So this the domain in which it converges is a disk of radius R is different, right? So the convergence of this series that we were talking about depends on these coefficients. Okay. So we considered that part of the series which only contains positive powers, which we considered for only positive powers for now. Okay, we'll look at negative powers after this, and then we'll see both together. For now, we're just looking at positive powers. But is this clear? Huh? Huh? Right? Fine. So this converges in this disk basically. If I write, so I'm doing everything around Z equal to 0. If you have at Z naught, then you have to center your everything around Z naught. Right? So right now it is mod Z less than R, then it will be mod Z minus Z naught should be less than R if you are expanding around Z naught, right? Because you should not go more than R away from this 0. There you should not go more than R away from what? Z naught. It's the same. So Z equals 0, okay? Obviously it's an analytic point, right? And then this series converges only when the radius is this. So in this domain, the function is what? Analytic, right? This function, which is equal to this series, okay? Okay, which is equal to. Outside, it just gives you infinite values. The series does not converge. Okay. I'll show you that outside, since this is equal to this, so there are two representations of this function. This representation and this representation. And the two representations are exactly identical only in this domain. When capital R is 1. Okay, same for there. Right? Because this would be 1 divided by 1 minus Z by R. It's the same thing with Z replaced by Z. Okay. So this representation of the function and this series representation are identical only when in this disk. Okay. We'll learn that outside there is a different representation of this function, and we'll learn the reason why we needed why there it would be different. Okay. But for now, just this is equal to this only when this, right? You can guess that okay, that this has to be the case. Why? Because outside mod z greater than r, let's say you take z here. Let's say you take z here. This series gives you what? Infinite. It gives you an infinite answer. It doesn't converge. But this, what about this? This gives you a finite answer. Right? It's just 1 divided by mod z minus r. It can't blow up. Right? Right? So outside, they can't be same. Right? Inside, they're same. We'll learn why that happens. Okay? Okay? Huh? For now, let's continue. Let's look at now negative powers. Okay? Huh? So let's consider f of z, because the series that we wrote has positive powers as well as negative powers. Let's consider f of z to be 1 by z plus 1 by z square plus this guy. Okay? Huh? Okay? What do you think this guy is? What do you think? When do you think this guy will converge? Exactly. Exactly. Right? Earlier you had z square, so you wanted r to be smaller. Now you are raising r, the mod of z, right? If I use polar representation, you will get 1 by r square, 1 by r cube. Okay? That will only become smaller and smaller only when r is what? Greater than 1. Right? No? Right? If r is 4, you will get 1 by 4, 1 by 4 square, 1 by, right? So this converges when mod z is what? Greater than 1. Okay? In fact, I can make this to be anything by r, z by r, z by r square. If I consider this kind of series, then mod z should be what? Greater than r. Okay? And this r and that r may not be same. I can just put r minus whatever. Right? Okay? Huh? So negative part, right, converges when mod z is bigger than some number. Right? Bigger than some number. R. And positive part converges less than some number. Okay? Huh? And what this number depends on, it depends on what your coefficients are. Right? It depends on what your coefficients are, what those integral values are. Right? How they change as you change n. Okay? Fine? This is fine? Okay? Now let's consider both of them together. Let's consider a series f of z, the Laurent series in its full form. So we have, let's say, so on, a minus 3 z cube plus a minus 2 z square plus a minus 1 by z plus a0 plus a1 z plus so on. Yeah, say a2 z square if you wish plus so on. Okay. Huh? So how many parts are of this series? How many? There are two parts. This part and this part. This part is this part is the one where non-analytic, if any, would come. If a's are non-zero, then z at z equal to the function would be not analytic. If a's are 0, then the function would be. Okay, is this fine? And this part is like the analytic part. This does not. Okay. Now, what about this part? When does it converge? This part. This part converges when mod z is what? Bigger than some r minus. Some r, some radius. Right? You just learned. Right? With simple examples. This has to be the same. Only thing is now I'm putting r minus because it will depend on these coefficients. Right? There I was manually putting it whatever I wanted to. Now these coefficients I have to figure out, and then that would determine what this r minus is. Okay. And this guy, this part, the analytic part, this will converge when mod z is what? Yeah, less than what? Some r plus. Okay. This guy converges when this mod z is bigger than some radius, and this guy converges when mod z is smaller than some other radius. Okay. When will you have a region where the series gives you finite answers? Because, right, if you don't have a region where the series gives you finite answers, then the series is pointless. It blows everywhere. blows up everywhere, right? When will you have a region where this series gives you finite answer? What do you think? What do you think? Which one? What do you think? Let's say r minus is 3 and r plus is 2. Then what? So r minus is what? 3. So I'll draw a circle around 3. Okay? Only mods are bigger than this, right? This part converges. This is 2, right? So only mods are this, bigger, smaller than this. This part converges. You know? Huh? So, but we have a sum of the two. Right? If a part doesn't converge, that means the full sum doesn't. It doesn't converge, but that may not be true entirely. But yeah, but if one this part, but for this it would be okay, because if this part doesn't converge, this part is finite. Right? If I take a point here, let's say, right? Okay, which part converges? This part converges, but this part doesn't. So the full thing won't converge. Okay, because this part is finite. It can't cancel it infinite. Huh? So is there any point where this series would give me finite answers? No. In this region, this converges, this doesn't. In this region, right? This converges, this region. In this region, same problem. No one converges. So what should R minus and R plus be? What do you think the relation between them for you to get at least a region where you get finite answers? What should be relation between the two? Exactly. So this should be bigger than that, right? So I should draw it like this. R minus should be smaller, and then you should get R plus. Right? Huh? And what is the region where this converges? What is the region? Ah, no, not this. Which region? यहाँ इस radius से इस radius तक, right? Right? So what is that? This? Yeah, exactly. This region, right? Okay. This is the region. Right? Whenever Laurent series makes sense, it converges in an annular region. This is called an annulus. Right? Remember? Right? It's just a name. Yeah, please come. Okay. Is this clear? Yeah? So mod z bigger than r minus and mod z less than r plus is satisfied here. In this region, both of them converge, and the full thing converges. Right? Huh? Outside, one of them diverges. This part or that part, the sum, and the other is finite. That's very important. Right? One of them diverges, but the other one converges, so the sum would not converge. Okay? Not converging means diverge. Okay? Huh? There are multiple ways a series can't converge. One is your terms are becoming bigger and bigger. When you are adding, they are becoming bigger and bigger, so it won't converge. Okay? Huh? But this is not the only way. There is another way if your sum oscillates. If your sum oscillates, then it won't converge. Right? For this case, that won't happen, right? Because you have this r here, r square, r cube, right? It will either grow or decay. Huh? In one case, the series would converge if it just decays, if all the terms just decay. Right? That's vaguely put. There is a way of making it precise, but we don't need to worry about it right now. For now, for us, the sum mod z within this annulus, right? This converges, that converges because the terms are becoming smaller and smaller. Okay, so where does Laurent series converge? It always converges in a annular region whenever it makes sense. Okay, huh? Okay, good. So did you understand this well? Because I need to use this idea in the next thing that I'm going to do. Okay. So we now have a full understanding of this series, right? Where does it converge and where does it not converge? Okay. Remember, the series converges here, but it's still an expansion around z equal to 0. Okay, you get my point? It might happen that r minus is just 0. Might happen. Okay. It might happen that r plus is just infinity. It could happen. That could happen. It's perfectly okay. Okay. Let me give you an example. E power z, I hope I get this right, is 1 plus z square, because this is analytic, so you can just use the real one, right? It's the same procedure. 2 factorial. So this guy, okay? Huh? So it has 2 factorial, 3 factorial, 4 factorial, whatever, n factorial. Okay. If you check its convergence, it converges for all z. I think, yeah, it does, because of these factorials. You are dividing, you are just not raising r to the power n, you are dividing with factorials, right? Okay. So this works everywhere. So it's obviously it's r. There is no non-analytic part, right? So r minus is just 0. It's just 0. It converges. Right? R plus is infinite. So this guy converges everywhere. Okay. Is that fine? And it's because of these factorials. And that once again I reiterate my point. These r plus and r minus depends on what coefficients are. Okay. Depends on what coefficients we have. Okay. And how did I guess that this converges everywhere? Is because if you forget about this representation of the function and look at this representation e power z, you know it gives finite answers everywhere. Huh? And this has to be equal to this because it's analytic and I can do those derivatives and all, right? And therefore this sum should always give me a finite answer. So r minus should be 0 because there is no non-analytic part, and r plus should be infinite because at every z it gives me it might give me a very big number, like at r equal to 100, at z mod z equal to 100, right? Whatever point, it might give very big answers, but it's still finite. It does not. Once you keep on adding, right, you might need to add a lot of them to get to the right answer, but it will be fine. Okay, to converge. Okay, now, okay, now let's move ahead. I'll use this idea in what we are going to do now. Okay. Let's consider a function. Let's try expanding a function, because what did we do so far? We did an analytic function. We expanded an analytic function. Good. We expanded an analytic a function which is analytic everywhere except at one point where we are expanding at z equal to 0. Okay. There it is non-analytic, and we saw the difference. Right? When it was analytic everywhere, it just contained even powers. Sorry, it just contained positive powers. Right? When at z equal to 0, it was non-analytic. It just contained what? Even positive powers as well as negative powers. Right? So this is the difference between expanding around a point which is non-analytic and expanding around a point which is analytic. Okay. Now we will expand around z equal to 0. Okay. We'll still expand around z equal to 0. Okay. But we'll assume there are some non-analytic points. Okay. So let's say there is a non-analytic point here, and there is a non-analytic point here, whatever. Let's take 2 of them because the arguments are basically same. So 2 is enough. I don't want to confuse you with. Okay. Right. We are expanding around z equals 0. That z equals 0, the function is itself analytic, or it may not be. You know what the difference would be. But there are some non-analytic points here, here. How do I go about it? Should I just write down the Laurent series and be done with it, or should I think a bit more? Okay, let's try to see. Okay, let me write down the Laurent series. What is the Laurent series? I have whatever. So I have sum over n a n z to the power n. N runs from what? Minus infinity to this is my f of z, right? This is around z equal to 0, right? And a n are given by what? dz f of z divided by z to the power divided by 2 pi r. This is right. This should be what? Around any closed loop which surrounds this. And what series you have depends on what a n you have. That's the only thing here to determine. Okay? Huh? Now let's look at this. If I take a loop here, right, then I'll get some a n. Huh? Now, but if I take a loop here, this is loop 1 and this is loop 2. Would the a n's be same? Remember, you are integrating a complex function, right? Would this, if I compute a n using this loop and I compute a n using this loop, would the two be same? Huh? Yeah, you are right. No, why? Yeah, the second one contains a non-analytic point. In fact, you see, if I compute, let's say if I compute a minus 5, huh? So that is what? 1 divided 2 pi I dz z to the power minus 5 plus 1 is minus 4, that is z to the power 4 f of z, right? Divided by z to the power minus 4, right? Okay, good. What is this on loop 1? Remember, f of z is analytic everywhere except this point and this point, these two crosses. 0, excellent, this is 0. So it means all negative. Like if I use loop 1, all negative coefficients will give you 0, right? Which is expected because this function is analytic within this loop, right? But if I use loop 2 to do this, it might not be 0, right? It might not be 0. Huh? So do you see what I am trying to say? That ANs are different here and they are different here. Right? So this function, whatever your function you have, okay, it does not have same series in this region and that region. You get two different ANs. You get ANs here are different compared to ANs here. Let's figure out कि ये वाले AN कहाँ है, मतलब ये वाले AN and ये वाले AN. So what do you think? What do you think? What do you think would be the? Let me use some other color, green. How do I change the color? Okay, with green I will mark what region. Okay, what do you think? Yeah, no, that's fine. So there would be two different. So you agree with me? There would be two series, two different series. Huh? Both of them would be valid in different regimes, right? Depending on whether you are enclosing this or not. Hai na? Huh? I want to figure out those domains. What regions are they? Okay. What do you think? What do you think? What regions they should be? So let me take any curve like this and any curve like this. Whatever region is bounded by these two curves gives the series given by this second contour, right? Whatever, so these curves should pass through these two non-analytic points. Let me call them something. Let's say Z1 and Z2. Okay, right? Whatever region is bounded by these two curves is the region where the two series given by this curve 2 would, right? Because I can deform curve 2 within this domain. I am not enclosing any new non-analytic point. ANs would be same. I will have the same series, right? Do you guys agree? Huh? Good. And the region inside this curve 1, right, would be what? Where I'll get series, first series. So let me call this series 1 and series 2. Series 1 works in first domain and series 2. Right? then if these curves are arbitrary, these two curves, okay, let me call them C1 and C2. If they are arbitrary, then the domains are arbitrary, right? है ना? Because I can expand, take this curve like this, then it would contain more points, right? Huh? What is the catch here then? What do you think these curves should be? What is the catch? What do you think? आपको क्या लगता है? Exactly, annulus, right? These two curves should be circles. Why? Because the function blows up here, right? So it means it blows up on any point with mod z equals z1. Mod z equals mod z1, right? Remember, we're essentially writing a Laurent series, and we learned the Laurent series always converges in a domain, annular region, right? Huh? Huh? So annular region की खासियत क्या है? If you annular region, what is the specialty about this annular region? That let's say you didn't know anything about the convergence, okay, but you were checking at some point, let's say here, you were checking at some point, let's say here, and you found out that the series is blowing up. So it means all the points inside or on the circle, it will just blow up. है ना? Same thing happens here. At Z1, you know that the function is blowing up. Why? Because there is an isolated similarity there. Okay? Is it fine? Huh? It means at any point mod Z less than Z1, mod Z1, whatever the modulus is here, it should just blow up. This series, the series which works in domain 2, that series. And at any point mod Z bigger than mod Z2, it should just blow up. Do you get my point? Huh? Huh? The series 2 is a Laurent series that converges on this annular region. Okay? And series 1, once again, a Laurent series, which converges in this annular region. Oh, well, this annular region is just a disk. Okay? Right? So how many series will you have? Let's clean this up a bit. How many series will you have? 2, are you sure? So if I have 2 non-analytic points, let's say here and here, right? And you're expanding the function around z equals 0, how many series will you have? So there will be one series in this region, right? Mod z. This circle is mod z equal to mod z1, where z1 is this point, and this point is z2. Okay? This circle is mod z equal to mod z2. Right? Huh? So how many series? So there will be a series which works in this region, region 1. Right? Because ANs are different. In this region 1, I can deform a contour without changing ANs. What else? This second one, between Z1 and Z2, the annular region between Z1 and Z2. Right? What else? Is there any other? You didn't? Yeah, the third series here. If you take a contour which encloses both Z1 and Z2, ANs will change again. ANs will change. They may also remain the same, but not all of them. Some of them will change for sure. Okay? Is this fine? And why was this an annular region? Because of Laurent series. Laurent series converges in an annular region. How many series will you have? Series representation to map out this entire function? 3. You get my point? So there will be one representation which would embed all these 3 series. Okay? But if you want to expand this function, you have to expand it differently here and differently here and differently here. And these would be pointwise equal to that representation, that one representation. Do you get my point? Is this clear? Let me give you an example. Okay. Now, okay, if you have one more analytic point, it's the same argument once again, right? How many you will have? 1, 2, 3, 4, whatever. In fact, inside the function is just analytic. Inside region 1. right? So it will only have positive powers, right? So all the formula that I wrote, remember I said this function has to be analytic everywhere. Now that has qualified a bit, right? It that formula, this formula, the differentiation formula, this one. Now what does the function needs to be? It needs to be in a domain where the function is analytic. You need to be in a domain, right? You need to be in a region of your complex plane where the function is simply analytic, which is indeed true here. You see, you yourself concluded that all negative powers will vanish inside. Okay, good. Let's do an example, and then we can end this class. Okay, I need to go. Let's do 1 divided by z minus 1, 1 minus z plus 1. Okay, let's do this only. This simple thing, 1 divided by 1 minus z. Okay, this function. This function. Simple. I'll do one more example. It's a bit more not trivial. So how many isolated singularities are here? One. Only one. Where? Z equal to 1. What is the order? Is it a pole? It's an essential. What is it? It's a pole. Pole of what order? It's a pole of order 1. Excellent. Excellent. Very good. Okay. It's a pole of order 1. Good. And where is it? At Z equal to 1. So let me draw. So how many series will this function have? Around Z equal to 0. 2. Right? So one would work in what region? Okay. And another will work in this region. Right? Huh? The one that works in this region, you already know that. Huh? You already know that. That is this. So let me call this F1. F1 of that. So this is the series that works in what? This is region 1. So this is region 1 and this is region 2. It is what? 1 plus z plus z square plus. Is this fine? Huh? You already know this, we just wrote it down, right? And F1 is exactly equal to f of z if you are where? Inside. If you are outside, no, not anymore. This blows up. This representation blows up. But this representation contains in it the other series also. I'll derive that. Okay, I'll derive that just now. Okay, but do you understand my earlier statement now? That there would be a representation of the function which would contain both the series inside it, right? But if you want to write a series, you have to work with different domains, right? And this is because of this Laurent series. It converges in another region. And plus ANs, you have to be careful. You can deform the contour of for which calculates AN. Okay, you can deform it only in a region without enclosing non-analytic points. Okay, and we figured out the only choice I have left, putting these two together, the Laurent series converges in an annular region, plus ANs, you can't enclose no new isolated singularities, right? It gave me that there should be another regions where things converge. Okay, okay. Let's do stuff. Let's do the series in region 2. Okay, in region 2, I just take. So what I do is I take mod z common here. So 1 by z. It will, let me take minus 1 by z common here. 1 divided by, what should I get? 1 minus 1 by z. Is this fine? This is, I have done that. It's the same thing. But this guy, I can expand. The same thing. Because I am where? Mod z bigger than 1. So 1 divided by mod z would be smaller than 1. So this is perfectly fine. So I can write it as 1 plus 1 by z plus 1 by z square plus 1 by z cube. Right? Works. So this is basically F2 of z. Is this equal to this? Huh? Yeah, it is. But where? Yeah, in this region. In the second region. You see, this representation contains both of them. But this series and this series have their domain of applicability. Okay? And it is pointwise equal to. Right? At every z, this will give you the same answer. Okay? Remember, these two series are very crucial. So you should remember this. 1 divided by 1 minus z is 1 plus z square plus z cube. Okay, is this clear now? So you see there are two series because there was one point. Okay, is this fine? And why did you get only positive powers in region 1? Because in region 1 there is no non-analytic point. So negative powers will vanish, right, by that formula, integral formula. Okay, one more point, one more example, and then we are done for the day. Okay, what about this 1 divided by 1 minus z plus 1 divided by 2 minus z, this function. So once again the same idea, we know the function in some representation, and then we are trying to write series of this function. Okay, if somebody directly gives you the series, okay, then I mean it might not capture the entire function. A given series might not capture the entire function, right? It might capture the function only in a certain domain. Okay, you just saw that this function 1 divided by 1 minus z is not captured by only one series. It's captured by two. You need two to map out the entire. You need to figure out the entire function. Okay, good. So how many poles? Two poles. Where? Z equal to 1 and z equal to 2. Right? So how many series should I have? 1, region 1, region 2, and 1. Is it fine? Huh? Okay. Yeah, I hope I am doing things rightly because I didn't prepare for this. Okay. Okay, let's do region 1. Okay. So in region 1, z is less than 1. What z? Mod z is less than 1. Well, z is less than 1 is a nonsensical statement. Why? Because complex numbers are not ordered, right? So mod z less than 1 because mod z is real number. Mod z less than 1 and mod z is also less than 2, right? You know? So I can just write it like this, f of z. I can expand this guy 1 plus z square plus so on. You know? You saw the series. This is plus I take 2 common, I will get z by 2, and mod z by 2 is less than 1, right? So 1 divided by 2, 1 plus z by 2 plus z square by 4 plus z cube by 8 plus 1. Is this a series? Yeah, perfectly valid series, right? Where does the series work? Inside, right? You see only positive powers. Why? Because in this domain there's no it's L, function is L in this domain. And I can put together powers if you wish. So 1 plus 1 by 2 is 3/2. And what is the coefficient for z? It is 1 plus 1 by 4. Then this is z. Something what 1 plus whatever 1 by 8 z square plus so on. This is not important. The important is that you get a series. Okay, let's do here. Let's do here. Okay, what should you do? So in region 2, mod z is bigger than 1. So I need to use this one. Right? Can I just not do it and just tell you what to do? You guys can do it at home. So in region 2, I need to use this one for this. But this one it still works. The same thing still works. This one still works. Right? Because mod z is less than 2 still. Or you take 2 common, mod z by 2 is less than 1 still. Okay? So what do I get? I'll get negative powers because of this. I'll get what was this? 1 minus 1 by z, minus 1 by z, 1 plus 1 by z square plus so on. And then I'll get positive powers, half 1 plus z by 2. Right? Okay, this is, let me call this f1. This is the representation of the function in the domain 1. Let me call this f2, and these are equal to f, but in their respective domains. Okay, outside those domains, these do not give finite answers, but the function is finite. Right? It's just that the function is, I'm repeating myself again, it's just that the function is captured by different series in different domains. Okay, and it's because of this non-analytic business. Is this clear? Plus so on. right? You see, you get powers 1 by z. Does that mean that the function has a that the function is non-analytic at z equals 0? You see, when you expand it in domain 2, you got 1 by z, 1 by z square, whatever. Does that mean the function is non-analytic at z equals 0? Why? No, that's plus powers are there. Fine, this is analytic part. Fine. Exactly. This is not in the domain where z equals 0 lies. Okay. The function does not have any singularity, any isolated singularity or pole or essential whatever at z equal to 0, right? So this is a bit deceptive while writing this series, right? It might suggest that at z equals 0, the function is what? It is not analytic, right? Because 1 by z, 1 by z square, right? In fact, it might suggest it has an essential singularity, right? But no. Why? Because this works, this is equal to my function only in this domain, domain 2, and there is no z equal to 0 there. It gives me finite answers there everywhere, right? In fact, the series does not converge at z equal to 0, so this series only works for, so that's why I need to write here, mod z is bigger than 1, greater than 2. Sorry, is bigger than 1, less than 2. Okay? Huh? Huh? What about the third one? What about the third one? Yeah, z is greater than 2. So I need to use this series for this and this series for this. This series in the sense that I need to take 2 out and then do the z by 2 business with while I iterate. Do you get my point? Or shall I write it down or is this clear? Huh? Huh? So I take, what should I take common? I'll take 1 by z common. I'll get something like this. Maybe I'll make an algebraic mistake. Minus 1 by z, 1 plus 1 by z plus 1 by z square plus so on. And then I'll take 1 by 2 common, or 1 by z common, minus 1 by z common, minus 1 by z. And what is the function left? 1 divided by 1 divided by 1 minus 2 by z, right? And this I can expand. 1 plus 2 by z, 2 by z whole square plus so. We're done. This is method. You can collect the powers of z. I mean, if you want to make it more. Okay. So now, do you understand this? Huh? Do you understand how to expand a function around? So even if z equals 0, even if z equals 0 was a singularity, let's say even if z equals 0 was an isolated singularity, even if there was singularity, still then there would be 1, 2, 3 domains, right? It's only that the only difference in region 1 you will have negative powers now to capture that singularity. Okay, if you had a function like that. Okay, that's the only difference. If z equals 0, the point where you are expanding was an singularity itself. Okay, huh? So do you know how? To expand a function now? We have multiple singularities. Okay, you just need to be careful which region you are in. You just need to be careful. Okay, huh? Quite often it will be obvious from the function that where the poles are. Okay, and then you need to be careful between what and what you are. Okay, yeah, okay, good. So this sort of, this sort of summarizes what I had to say about this Laurent series and where it converges, where it doesn't. In next class, we'll just do examples, okay, to calculate residues, okay, examples to calculate residues, and we'll do examples how to integrate functions, real functions, okay. Maybe we can end today.